Okay, welcome everyone to my new lecture where we are going to learn how AC alternating current is made. How can you make AC current? Okay, so here we have here a conductor like so. See, and the end of the conductors are connected with these metal rings. When I'm gonna show you why this is a generator. Generator is a machine that produces from mechanical energy to electrical energy. So this is a generator and it spins around. And in my next lectures, I don't know when that is gonna be, I'm gonna show you the principles. So for now, I'm just gonna show you how we produce AC. I'm not gonna explain you why do we have here metal rings and why do we have here brushes. So here we have two metal rings that we call slip rings. And we have here brushes that always stay on these metal rings here. So they slide on these slide rings. These slide rings rotate and these brushes always stay there. So, okay, we have a conductor that is now in the magnetic field. For example, here you have a north pole and here you have a south pole. Because magnetic induction goes from north to the south pole. Just imagine that you have magnetic field lines. Yeah, and if you didn't watch my previous lecture where I learned you what is the induced EMF, what is induced voltage, and direction of that EMF, I prefer that you go back and see that lecture. So this conductor is gonna spin around. So what we use right hand rule. So this side of conductor, this side goes in that direction. So the thumb shows you the direction of the velocity of this conductor. So it goes, I don't know, in this direction. Okay, so thumb shows you the direction of the movement of this conductor. So okay, in the palm of the hands are going into the palm of hands are magnetic induction field lines, like so. And these other fingers show the direction of the induced EMF. So if it goes like this, if this conductor goes in that direction, then you will have an EMF goes from here to here. Also here now, this side of the conductor goes at the blackboard, this side goes to you. See, the thumb shows the movement or the velocity of the movement of this conductor, like in so. Magnetic field lines come into the palm and the EMF shows here. So, in the electrical circuit, now this would be a minus sign here, and this would be a plus sign. So when you can, so now like a battery or generator in electrical circuit, this will become a plus, and this is going to become a minus sign, like so. Why? Because the EMF looks from the minus to the plus sign, like here, from the minus to the plus side. It goes from the minus to the plus side. And if you attach your here voltmeter is going to show you that there is an induced EMF. So here we connect parallel on these brushes voltmeter. But if you move this voltmeter and put a resistor here, then you will have a resistor, then you will have a current going from plus to the minus, from A to B. This is A, B. This is brush A, this is brush B. So here, brush always stay here, slip rings rotate with this conductor. So the current will go from A to B. Okay, so that's one direction. In my previous lecture, I explained that alternating current always change the direction. So here is the next situation. Now, this conductor that was here moved up here, and this that was here up here is now down here, and now we have another situation. Okay, so this is going in this direction. Oh, it always goes in one direction. Okay, it won't always in generators, in motors, you have I'm sorry, in one direction movement, because if you have a rotor or a generator that goes like this, then it's not, motor. Motors, you use motors, for example, for your cars, to move your cars, or you also have electric cars, not only that goes on diesel or gas. For example, I don't know, when your vacuum cleaner always goes in rotation. So all generators and motors go in one direction. So now this side goes here, that was connected to A. So okay, DMF is always going to show in the same direction, but now the A becomes minus and the B becomes plus, because now here the A side is this side EMF is stayed in the same direction, because this is going to go in, this side of the conductor is going to go into the blackboard. So tab shows you the blackboard. Magnetic fields stay the same, they come into the pump, so the EMF is going to go like this. So this becomes minus and this becomes plus. So here you had the A was plus and the B was minus. Now when you have a circuit like this, now this side becomes plus, so the brush of B becomes the plus sign, and A becomes the minus side. You put a resistor here, not a voltmeter, and then the current will go in the other side. So that is the basic principle of alternating current. It changes the direction. Okay. So now I showed you now I proved to you that alternating currents change the direction. Okay, I now must show you and I must prove you that alternating current changes its intensity. So it's not always 10 amperes, for example, like in DC. When you have DC, you always have 10 amperes. But in AC, you don't always have one steady current. It changes through time. So let's put a north side here. Let's here put a north pole of a magnet here and a south pole here. This 1, 2, 3, 4, 5, 6, 7, 8, 9 is not how many magnets you have. This is always the same, north, south. So that don't be confused. This is always. One is the situation when this conductor is in this situation. 2 is when is this. Okay, so this is the situation. North and south always stay the same. So, and let's say it goes like this. It starts to rotate in this direction. So, number 1. Okay, so in number 1, in situation number 1, you don't have induced EMF. Why? Because it starts to rotate in this direction. Okay, so the thumb shows you the direction of the movement of the conductor, like so. It goes up. But as you can see, none of these magnetic inductions none of these magnetic inductions goes into the palm of the hand. So you don't get any EMF induced in this conductor at this position. So you must look in which direction it rotates, and does it go any EMF? Does it go any magnetic induction into the palm of your hand, like so? You see, none of this would go into the palm of your hand. So here we have okay. So here we have an EMF. This is the EMF axis, and this is time. Okay, this here is time. So at time number 1, you have 0 EMF inducted. Now this conductor here is gonna go at this direction. Okay, the thumb. So the thumb shows the direction of the. So okay, sorry. So then the movement of this, the velocity is going to go in this direction. So now you can see that that it's gonna go like this. You see, it has an angle, and some of these magnetic induction are gonna go into the palm of the hand. Some not, because I made the angle like so. You see, it goes like this. Okay, thumb shows you the hand, and you see some of this. Now when it goes like this, the thumb shows you the movement of the conductor, and some of the magnetic induction field lines go into the palm of your hand. That's all. So in situation number 2, you have EMF produced this value. Okay, I think that's correct. So in number 3, you have the maximum. Why? Because the velocity, the movement of this conductor is perpendicular to the magnetic field lines, as you can see here. So thumb shows the direction of the movement of the conductor, like so. All of these magnetic induction go into the palm of your hand, like so, and then you have the highest and the maximum value of the EMF. So you are going to have the maximum value of EMF when you go perpendicular to the magnetic field lines. Okay, so now this here you're gonna go in this direction. See, it goes in in this direction. So thumb of the hand shows you the movement of this conductor, and as you can see, some of the magnetic field line, the value of here and here are the same. So here in situation number 4, you have the same situation number 2. And here, because the movement of the conductor is in the same direction as the magnetic field lines, as you can see, none of the magnetic field lines go into the palm of your hand. So then you have 0. Okay. For example, see here, this side. Let's take it that this was this side. So now the next situation is that here we are gonna have the same here. Now here you're gonna have the same value, but in the opposite direction. So the EMF it's gonna be the same situation here. It's just gonna go in this. It's gonna be in the other side. The EMF is gonna show you the other side. Now you have EMF going from here to here. Now it's gonna go from here to here again, but you just change the side of the conductor. Same as here, as you can see. So you're gonna have a same situation, but you just change the side of the conductor. And you changed the EMF. Like we had this situation. This was plus, this was minus. And when you made 1/2 of the turn, now this becomes plus and this becomes the minus. So here you have 1/4 of the turn, full turn. See, because here you have as you can see, that is the full turn, full rotation, one rotation. We calculate the one rotation. And okay, so 1 period is the full rotation of this conductor, and at 1/2 and 1/4 of the period you have the maximum value of the EMF. At the half of the period, 1/2, as you can see, 1 divided by 2 is 1/2. You don't have any EMF. And 3 divided by 4, and 1 period you came to 0. So 1 rotation is 1 period. And now you saw how this changes. Here and here is the same value of volts. Okay, the same value of volts. And you know, it's just this opposite side. Okay, don't be confused. This is minus 215. This is plus 215. It's the same value. Those plus and minus in electrical engineering, it just means it's in the opposite direction. Okay, so okay, but how does this affect current? Well, it's easy. For example, in period number 2, you have voltage, I don't know, 100 volts, okay? And when you put 100 volts here, and you have a resistor, 10 ohms, okay, 10 ohms, then you have the current, Ohm's law, voltage divided by the resistor, 100 divided by 10, then you have 10 amperes. Here you have 200 volts, here you have the maximum value of the current. So here you have 200, yes, and then you will have electrical current that goes 20 amperes. This is the maximum value of the current when you have the highest EMF, okay? So here you have 100 again, so this becomes 100. Okay? Here you have minus 100, and then you get minus 10 amperes. It just means that the current went in the opposite direction. See? Here was, the plus, and here you have the minus. Okay, you get the point. Current changes its value because it changes the value of its EMF. Okay, you got it, and okay, 1 period is a rotation, but how do you calculate what was the time of that of 1 period? Well, if you're in USA, all of your generators and motors have a frequency of 60 Hz in USA. What does that mean? That means that in 1 second, this generator here is gonna make 60 rotations. Okay? So the period, let's say the period is capital letter T, and the frequency is frequency. So frequency is number of rotations in 1 second, okay? Number of rotations in 1 second. And a period is okay. The period is one rotation, but calculated in seconds. So if you have, I don't know, we in Europe have frequency of 50 Hertz. So our power plants have generators that go around 50, that make 50 rotations in 1 second. So in 1 minute, that is 3000 rotations per minute, in 1 minute. And if you're in USA, all your generators make 3600 rotations in 1 minute. So if you want to calculate what is the period of this induced EMF in the conductor, then the formula is, let's show you, 1 divided by F. So if you are in Europe, then you have 0.02 seconds, because if you're in Europe, 1 divided by 50 is 0.02 seconds. If you are in USA, that's 0.0118, I don't know. And okay, so what does this mean? That means that if you turn a light bulb, then in the moment when the EMF is 0, then you will have, then the light bulb is not going to glow. And 0.1 seconds, it is going to glow, and then it is gonna, and then it won't shine again. Then it won't glow again. And if you have and the next 0.1 seconds, 0.01 seconds is gonna glow, and it's not gonna glow again. But in electrical engineering, that's not the case, because you always see your light bulbs glow. There's a lot of more stuff and to see, and your eye cannot register this high frequency. Your eye can register 25 Hertz. So 50 Hertz and 60 Hertz are big values in electrical engineering. So I think I gave my best to explain this. My English isn't very good, as you can see, but I really tried my best, and I thought I learned you what is the principle of alternating, how alternating current is made, what is the genesis of AC. This is what Tesla. This is how Tesla made AC. Okay, so thank you very much for watching my lecture. See you in my next lecture, where you are going to learn how do we measure alternating currents. What do we measure alternating currents when it always changes its value? See? Always changes, but I'm gonna show you how in electrical engineering that problem is avoided. Thank you for watching and see you in my next lecture.